But
Right.
y'all
Isn't there one here?
Alright, so guys, let's focus on the class. Last time we started talking about the flexibility method, and I know I threw a lot of information on you, but I like to explain the concept. But in general, the flexibility method, it's an extension of the virtual work method. I mean, like, we use the virtual work method to do the basic analysis for the flexibility method. But let me get the ground base of what we need to do with this. Okay, so the thing is, flexibility method is a method to solve an indeterminate structure, and as I said last time, indeterminate structure is going to be something like this. If it's a cantilever, I will be able to solve it, but it's not a cantilever. There's a hinge or a roller here, okay? So I can't solve it, but we can make this into two beams. Like, we can say that this is like, if it has this load, W, I can say that this beam is something like this, is a cantilever, plus a beam like this that has a reaction F, right? But the thing is, to this to be equal this and this, the deformation from this beam, which we call it last time delta 1O, should be equal the deformation, I like to be precise here, the theta is equal to 0, and then we go here, should be equal to the deformation that we have from here, we call it delta 1, 1, right? Or we call it delta 1, 1 multiplied by F. Like, let's put this one, it's the same thing, right? So if I put unit load, this unit load is gonna give me delta 1, 1. If I multiply it by F, it's gonna give me the same thing. Or I can put F here, and here this is gonna be equal delta 1, 1, the big one, all right? So the thing is, if I did this plus this, is gonna give me this, right? But for this to be applied, the compatibility equation need to be satisfied. What is the compatibility equation? The delta 1O, this amount of delta, plus delta 1, 1, which is F, small delta 1, 1 equal to 0, right? So that's what we agreed on last time. This is two beam, this beam and this beam. But for this to be satisfied, this force needs to induce a deformation equal to this deformation so that we end up with 0 deformation at this point, because there is hinge and there is no way for this point to move, right? So that's actually the concept of the flexibility method. That we come up with a main system that is determinant and stable, and I can solve it. What do you mean I can solve it? I can get reaction, I can get bending moment, shear, everything. And I put a unit load at each removed redundant. Like here, this is a removed redundant, I mean like removed support. I put a unit load and I multiply it by F. So it's up to you. If you want to keep it F as is and deal with delta 1, 1, that's fine. If you want to make it unit load, the final deformation that you get for the unit load multiplied by F. Why is that? Because let's say if one unit load is going to induce 1 centimeter, so if the final force F is equal to 10, so it's 10 multiplied by 1 is going to be 10 centimeter, okay? So we're going to put a unit load, and unit load is going to produce a delta 1, 1, and then if we multiplied it by F, which is the reaction here that we are looking for, is going to be the same thing, all right? Are we agreed? Okay, let's come to some definitions. What delta 1O mean? Delta 1O, the 1 means the point that we put the unit load at. So we say that delta, this is delta at point 1, which is this one, we call it number 1, due to the original loads. Original loads, they mean like if there's a concentrated load, I'm gonna put it here. If it's a distributed loads, I'm gonna put it here. Delta 1, 1 means at point 1, this is the first one, and the other one is due to unit load at point 1. Okay? All right, so the O means the original load, the 1 means the unit load, the one at the end. The first one is that the same point that we're looking at. It's at point 1, and both of them are at point 1, because sometimes, like in a few minutes, I'm gonna put a beam that has multiple supports. So we have point 1, point 2, point 3. Okay, so you are gonna understand it in a little bit, but this is the main equation. But is that simplified from last time? Do you guys understand it? Okay, so what if this is not a hinge? Like I have a spring here, and I opened the discussion about this last time. So, and I have the same load. So it's gonna be the same thing. What is the main system that I can have here? By the way, here I choose the main system cantilever. You can make the main system simple beam. Like you can make it this way, and you keep the roller. That's my main system, right? Okay. But here, right now, I removed the moment. So when you remove the moment, so that second beam is gonna be something like this. And then you put the unit load, 1 unit load here, rather than here. Because here I said that I released, like here theta is 0, right? But when I release the moment here and make this system, here this theta is not gonna be 0, right? So I need a force, a moment that can counter this theta to make it 0. So I assumed it 1, but actually it's gonna be at the end m multiplied by 1, and I wanna find the value of m. So I wanna find the value of the moment that is gonna bring the theta here to 0. Like, this is how the final deformant shape should be look like, right? But when I made the main system like this, theta here is not equal to 0. So I need to find out what is the value of the moment that I put here that can bring this theta to be 0. And at the end, we will end up with like theta 10 plus m that I'm looking for, theta 11 is equal to 0. That's the other equation. How can I find theta 10 from this system? How can I find theta 11 from this system? I draw the bending moment here, and I draw the bending moment here, and I use the concept of the virtual work to do it. We are gonna have some examples so that we can know how to do it, and I'm gonna put the steps how to solve the flexibility method. This we call it like method of consistent redundant. How to solve using this method. All right, so we are done with this part, but what if my beam is something like this? There's no roller, there's a spring, and this spring has a stiffness K. It is the same thing like this one, but like you're gonna have a cantilever, and then you put a unit load, but at the end, the compatibility equation, at this point, this system, when it's gonna deform this point, the displacement is not 0. It's only 0 if this stiffness is equal to infinity. So the deformation is gonna be something like this. It's gonna be, and then it goes, and then there's some residual displacement here. This residual displacement is equal to delta, and this delta is equal to F over K. What is the value of F? Is the reaction in this spring. And what is K? Is the stiffness of this spring. If the stiffness of this spring is equal to infinity, delta is going to be equal to 0, because F over infinity is 0. Okay, so at the end, when you have the equation, delta 10 plus F, here, this equation, plus F delta 11 is going to be equal to delta inside the spring. And the delta inside the spring is F over K, and it's going to be negative because my positive direction is F going up, but delta of the spring is going down. Every spring, the deformation in the spring is in the opposite direction of the force. Like let's say, like this spring is under compression, so delta is going down, the force is going up. But if it's under tension, force is going down, delta is going up. So they are always in the opposite direction. So this is always negative. Same thing if you put the beam like this. Like let's say our beam is something like this, and you decided to go that way, that route. So what I'm gonna have, no, this one, there's no roller here, so it's gonna be difficult. So this is the best way to solve this problem. Because if you have this here, and if you choose to remove the moment here, this is really gonna be a tough problem. Because when you are gonna get the reactions, you have to deal with some stiffnesses. So my best way to deal with it is that I remove the spring. If you have a problem that has a spring inside, so always try to remove the spring from the problem, make it the unknown, and deal with the other supports. Okay. All right, is that clear? So let's actually put it step by step, how to solve method of consistent deformation problems. Steps. Well, number one, determine the degrees of indeterminacy. Degree of indeterminacy. Number two, choose main system. And this main system needs to be stable and determined. Number three, draw the bending moment diagram for the main system. Let's call it MS, main system. And this main system with original loads. And this bending moment diagram, we call it MO. All right? So number four, put unit load at the removed redundants. Then draw the bending moment diagram and then get what we call M1. Number five, calculate the deformations. Delta 1O and delta 11. Number six, apply the compatibility equation. Which is delta 1O plus F delta 11 is equal to 0, or delta depends on your problem. And at the end, if we want to draw the final bending moment diagram, you're going to have a bending moment diagram from this beam. Like, let's say, okay, let's go through step by step. Degrees of indeterminacy. I know that this beam has a one, like, redundant, right? It's 1 degree indeterminate. So that's the first thing that I decided. And I decided to choose this as a redundant. I'm gonna remove the support. So I did number one, choose a main system. I choose the cantilever as a main system. I remove the redundant and I choose a main system that is stable and determinate. Stable and determinate. Okay. Number three, I draw the bending moment diagram of this. The bending moment diagram of this beam is something like this, and it's negative, and this is WL squared over 2. That's the bending moment diagram. Number three, put a unit load at the removed redundant. Okay, I take this beam, I removed all the loads, and I put a unit load, and then draw the bending moment diagram. The bending moment diagram here is positive, and it's linear because it's a constant load, and it's gonna be 1 multiplied by L, and this is positive. You guys know when it's positive, when it's negative, right? Mm-hmm. We know the signs of the bending moment. All right. Okay, so I drew the bending moment diagram for the, I put the redundant, and then I got M1. So this is MO, and this is M1. Number five, calculate the deformation delta 1O. Do you guys remember from the virtual work, if we have a beam that has this load, how we calculate the deformation? For this beam, we did it before. Like for this beam, if I want to find the deformation here, first you have to put a unit load at the location that I remove all the loads, and then I'm gonna put, for example, a unit load like this, 1, and then I draw the bending moment from this beam, like let's say the bending moment is something like this, and I draw the bending moment for this beam. This is MO and this is M1, and then I found out that the delta, if I want to find the delta here, it's gonna be something like this, going up, because I put my loads or something like going this way. Well, no, it's not like that way. That's negative, and that's positive, right? So I have to take care of those. I use the tables, and do you guys remember the tables? It's gonna be delta, and that's 1O, because this is O and this is 1. So delta 1O is gonna be the integration of M1 MO dL over EI. And I take 1 over EI outside, and then I integrate M1 MO dL. I use the table, and then I found out this value, right? So this is how I can get the deformation delta 1O from this load, right? I do the same thing to get delta 11. Delta 11 is a system like this that has a unit load, right? If I want to find the deformation here, I remove this one load and then draw another one and put another unit load again, right? Because I want to find out what is from this. It happens to be that the main system here is the same as the virtual system. Like, let's say, for example, our virtual system method is you have a beam, has a specific load, okay? You draw the bending moment from the original load, okay? So our original load is unit load. And then I remove all the original loads and then I put unit load, which is this system. So it happens to be that this is M1 and this is also M1. So if you want to find delta 11 that comes from this and this is going to be the integration of M1 dL over EI. I do the same thing. This is going to be positive and this is going to be positive. So 1 over EI and then I integrate M1 dL. By the way, always delta 11 is positive. Why? Because this system is the same like this system. If this is negative, this should be negative. If this is positive, this should be positive. So if M1 positive is going to be positive, negative is going to be positive. Okay? So delta 11 is always positive. But delta 10 depends. This is negative, this is positive. So definitely this is going to be negative because I have negative multiplied by positive. All right, so I got delta 10, I got delta 11, and then I calculated the deformation delta 10 and delta 11. Then I apply in this rule, delta 10 plus F delta 11. So if you want to times F is going to be negative delta 10 over delta 11, and then you got the missing reaction that you are looking for. Okay, number 7, because this is one of the questions that I'm going to ask you. Once you get the reaction, I want you to draw the bending moment diagram or the shear force diagram. So draw internal forces. Internal forces, so the final internal forces, the thing is, we have a bending moment from the original system and from the virtual system. But what is the final bending moment of the beam? It's gonna be a combination between this system and this system. And how it is gonna be? MF is gonna be equal to MO, like this moment, plus F multiplied by M1. This plus this multiplied by F. Why? Because it's a combination between this system, and I know that this system is just from the unit load, but if I wanna find the one corresponding to F, I need to multiply F by this system. So this bending moment plus this bending moment is gonna give you the final bending moment. How can I do that? You find, for example, if you found the bending moment here is 5 and here is 1, so it's gonna be 5 at this point plus F multiplied by 1. Here is 0 and 0, so it's gonna be 0. And then you connect the same way. We are gonna do it in a little bit, but I'm just showing you the steps of how we can do that. Does anybody have any question so far? All right. So just for you to understand, I'm gonna expand what I did on a much bigger problem. Let's say, just to confirm that you guys understand everything, let's say that I have a beam, and I have a roller, and I have a ruler, and another one, and another one. How many degrees of indeterminacy are we dealing with now?
3.
3, right? So, I mean, like, there's 3 redundancies that this system doesn't need to be stable and determinate. If you apply the rule, you will find this 3, they are not needed. Okay? So, how can I deal with it using this method? Let's do it step by step. The first step I did right now, I decided or I calculated the degrees of indeterminacy, right? So it's a 3. Second step is I choose a main system. What is the easiest main system that I can deal with now?
Simple span.
Simple beam, and I remove this 3, right? So, okay, I'm gonna, all right, I'm gonna make something like this. I put hinge here, roller here, and I remove this 3 because I don't need this 3. So my job right now is to find the reaction F1, F2, F3, right? That's my job, to solve this system. Once you find them, you put them as a load and then find the other reactions by the static equation. Some Fx, some Fy, some the moment about z, you will be able to find these. But without these 3, you will never be able to solve because you have 5 unknowns, not 5 actually, maybe 5 because the X reaction here is 0. So you have 1, 2, 3, 4, 5, and you have only 3 equations. So it's not gonna be, you are not gonna be able to solve it. So you need to find what is the value of these reactions. Okay, so I'm using the flexibility method or the method of consistent deformation to find these 3 reactions. I decided the redundance, then I choose the main system, it's determinate and stable. Let's say that this system has a general load, like let's say that we have a distributed load here, and then I have a concentrated load here, and then maybe concentrated moment here, okay? So I put all the original loads in the same locations, same everything. And what is next? You find the bending moment from these loads, okay? So let's say like my system is gonna be something like this with deformation. Let's say the deformation is gonna be something like this. That's deformation. All right, let's see. When we had it here, we said that the deformation here is delta 1O, okay? So right now I have 3 points. I have 1, I have 2, I have 3. So I have delta here that is delta from the original loads, right? Like this one. On the main system, so delta 1O. So here, this is also gonna be delta 1O. What does it mean? Delta at point 1 due to the original load. Point 1 due to the original load. So you guys tell me, how can I name this point? Delta what?
2O.
Delta 2O at point 2 from the original loads. How about 3O? Okay, so this is all the deltas. And next, let's see. Put a unit load at each removed redundant. Let's put the here at each removed redundant, not that each. All right, I'm gonna make a system like this, and I'm gonna put a unit load. I know that the reaction is going up, so I'm gonna put a unit load here, F1 kips or 1 feet, okay? And then I try to find the deformation. Actually, here I put them go up there. You can put them down, up, whatever you want. At the end, if you put them in a wrong way, it's gonna be negative. That means that you assumed in the opposite direction. All right? So the deformation here, let's say it's gonna be something like this, right? All right, you guys tell me, you'll tell me, okay, you only put a unit load. How about the other unit loads? Everyone have to be separately. So like I have to make 3 beams and another one here. And I put a unit load here and a unit load here. 1, 1. At each remove the redundant. And from each one, you are gonna get a deformed shape. Okay? It's gonna be something like this. You guys tell me, what is the value of the deformation here? Based on what we learned from there. I'm gonna tell you. This is delta 1 at point 1 due to unit load at 1. Okay? This is delta 2 due to at point 2 due to unit load at 1, and this is delta at point 3 due to unit load at 1. Let's come here. Here, it's still delta 1 due to a unit load at point 2. How about this one? Delta 2. It's at point 2 due to a unit load at 2. How about this one? Delta at point 3 due to unit load at 2. How about here? Delta 1, 3. That means that this is delta at point 1 due to a unit load at 3. And this is delta 2 due to unit load at 3. And this is delta 3. Okay? So that's how we do it. At the end, like once we solve this problem, delta 1 plus this delta multiplied by the value of the reaction here plus this should be equal to 0. Okay? Why this is a compatibility? Because at the end, the deformation here should be 0. So if I remove all these supports and I let this goes down, it's gonna give me delta here. So the reaction from here affect the delta here, and the reaction from here affect the delta here. So how can we take all these effects? This one is gonna make delta 1, 3. This one is gonna make delta 1, 2, delta 1, 1. And the sum of all the three of them plus this should be equal to 0. That's the compatibility. And this is how we are gonna get three equations. Look at this. At the end, delta 1 plus F1, the reaction here, delta 1 plus F2 multiplied by this one, delta 1, 2 plus F3, delta 1, 3 should be equal to 0. How is that? This deformation plus this deformation multiplied by the reaction here, plus this deformation multiplied by the reaction here, plus this deformation multiplied by the reaction here. Because at the end, this is only a unit load, not the final reaction. Okay? So at the end, this one should be multiplied by F, but we don't know F yet. So that's why we'll put a unit load and keep F outside as a constant. Because you can draw the deformation from a unit load, but you can't draw it from F, because F, you are going to make your entire problem as a function of a variable. It's going to make it difficult. So we take F as a common factor, and we get the deformation from 1. So this is only equation 1, because we know that the support number 1 has 0 deformation. We can do the same thing at point 2. So you can say that delta 2O plus F1 here multiplied by delta 21 plus F2 multiplied by delta 22 plus F3 multiplied by, okay, now I'm confused. So F delta 21, 22,
3.
F3 delta 2, 3, 0. Okay, let's focus again. All right, so I have 1 multiplied by delta 21, 1 multiplied by delta 22, and F3 multiplied by delta 23. So it's the 3 deltas here. So all of them has 2 adverse. Like look, if there's 2, 2, 2, 2. This is 1, 1, 1, 1. All what is it changing? 0, 1, 2, 3. That means that unit load, no load, original load, unit load at 1, unit load at 2, unit load at 3. Same thing, delta 3O plus F1 delta 31 plus F2 delta 32 plus F3 delta 33. Make sure that you have here a line 1, 1, 2, 2, 3, 3. We can put this at the end in a vector format, like you can put this like this, delta 1O, delta 2O, delta 3O, plus a matrix that has and all of this is equal to 0. this is how we solve this problem. We build them as a matrix, and then you put the matrix on your calculator and then solve this matrix. So if it's gonna be 4th degree, it's gonna be more difficult. 5th degree is more difficult. That's why it says that this method is very good when you have 3 levels of unknowns. After that, it's gonna be a little bit of a struggle to solve. Do you guys understand it? Okay. All right, I put something here to generalize the approach. Delta I J. Do you guys understand what is I now and what is J? Like here we put a number and here we put the number. Based on your understanding, what is this number?
The point.
The point that we are dealing with. So this is that means delta at point I. How about the other number? This is where the unit load at unit load at J. Okay? So this is the point that we are measuring the deformation at. So that means, let's pick this one. This is point 1 due to a unit load at 2. This is point 2 due to a unit load at 3. Okay? By the way, if you look here, look at this. You always have, if this is delta 1, 1, you need to find M1 and M1. If this is delta 1, 0, it's gonna be M1, M0. Let's pick delta 3, 2. Delta 3, 2, you need to find, it's gonna be the integration of M3, M2, DL over EI. You integrate the bending moment from system number 3 with system number 2. But let me tell you something. The general rule of delta ij is something like this. Delta ij is equal to the integration of ni, nj, dl over ea plus the integration of qi, qj, dl over gar. Gar. And this is actually x and this is y. Plus the integration of qi, qj, dl over gar, and this is y, plus the integration of mi, mj, dl over ei, plus the integration of mi, mj, dl over ei. This is x, this is y, x, and this is y, and the integration of the torsion Ti, Tj, dl over G, I, T. That's the general equation of the delta, because any beam can have 6 forces. Can have shear X, shear Y, moment about X, moment about Y, normal and torsion. This is the 6 internal forces that all of them contribute to the strain energy. But as I said to you before, when a beam has a vertical load, most of the deformation comes from the bending about this axis, which is usually the moment about X. So once we calculate all these deformation, you will find that the contribution of all of these plus these is like less than 5%. And this one contributes by 95% of the deformation. And the other one is like less than 5%. So that's what we talked about, that we need, rather than spending half an hour solving for this and half an hour for solving for all of this, we can, that's what I did actually. I have a problem here that I'm gonna solve in a little bit. I did it for normal shear and moment. That's how I solved it here. Yesterday when I tried to solve I only did it for moment, and it didn't make any difference to the numbers, because the other numbers, like it's 10 to the power negative 5. But the comes from the moment is like 0.95 or something. So that's what I was trying to say. So usually that's why we only include the bending moment, unless we are dealing with a truss. The truss doesn't have a bending moment. All the deformation come from the normal, so 100% of the forces are here. The normal force, and that's the problem in the quiz. Sorry, the problem in the homework. Okay, so yeah, it's in the quiz. Yeah, just saying.
No, is it the first line? Is it EA or EI?
This one is EA.
Okay.
Normal force is only about the cross-section area. The moment is about EI. Here it's called GAR. AR is like there is a table in the textbook. It's called a reduced area. Like AR is alpha multiplied by A. It's a reduced area for shear. And G is something in relationship of the Young's modulus and the Poisson ratio of the it's called shear modulus. This one. So the textbook, the fundamentals of structure analysis, the one in the syllabus, you can find how to calculate this one. And IT is the total inertia of the cross section, which is IX plus IY. So because when a torsion happens on a section, both inertias are included. So yeah, it's I believe you guys take if you guys have a class in advanced mechanics of materials, you will know all this information. But let's focus on only the moment here in my class. One thing that I want to mention is the value of delta 1, 2 is equal to the value of delta 2, 1. And the value of delta 1, 3 is equal to the value of delta 3, 1 as values. Same thing, delta 3, 2. So when you swap the numbers, they are always the same. So you don't have to calculate, if you have a problem, you don't have to calculate delta 1, 3 and delta 3, 1. Both of them are the same, so you only calculate one. This comes from a theory. Let me write it over there. Well, that's actually makes sense. Like here, if you are integrating delta 1, 2, you are gonna integrating M1, M2. M2, M1 is not gonna make difference because you just swap the equation. But this is actually, it's a theory, you will find it in the textbook. It's called Maxwell-Betti reciprocal theory. Maxwell-Betti reciprocal theory. This theory is saying, like, if you have a beam and you put like these 2 points, if you put a load F, let's say F1 here, and the same beam at point 2, you put F2 here. This is gonna give you a deformation. Here's the deformation, it's delta 1, 1. This is the deformation, it's delta 2, 1. This one is gonna give you a deformation, something like this. This is delta 1, 2, and this is delta 2, 2. F1 multiplied by the deformation from the second load, delta 1, 2, is gonna be equal to F2 multiplied by this one, delta 2, 1. But the thing is, in our case, F1 and F2 are 1 unit loads. So if F1 is equal to 1 and F2 is equal to 1, so delta 1, 2 is equal to delta 2, 1. So if I have a problem that has 3 degrees of indeterminacy, basically I have to calculate these 3 values, delta 1, 0, delta 2, 0, delta 3, 0. So I integrate the bending moment from the original system with 1, and this was 2, and this was 3 to get these values. And then I integrate delta 1, 1 with itself, and delta 2, 2 with itself, and delta 3, 3 with itself. So I can get the diagonal here, okay? Then I do this one, and this one, and this one. And right now I solve it for all the unknowns. Why? Because these 3 are the same like this 3. Okay? It's a lot of number to calculate, so in the exam, I wouldn't give you something that is 3 by 3, maybe 2 by 2 maximum, okay? So that you can solve 2 equations and 2 unknowns, so you don't have to build a matrix. All right, we have half an hour. Let's solve an example. Is everything clear till now? Any questions? All right, so if I have a frame like this, and it has a load 6 ton here, and a load 3 ton here, and this distance is 3 meter and 3 meter, and this distance is 2 meter and 2 meter. And I'm asking to draw internal force diagrams. Let's say draw bending moment diagrams. For the reinforced concrete frame shown, and the cross section is rectangle, so we are talking about cross section of the frame is something like 20 centimeter by 40 centimeter. And the E, Young's modulus is 210 ton per centimeter square. I give you a Poisson ratio of 0.2, but we don't need it, but you will need it here for the example that I have here because I calculated delta that comes from the normal shear and moment, but right now I'm only calculating the moment, so I don't need the Poisson ratio. Okay, so let's solve this problem. You guys tell me step by step what I'm gonna do. Degree of indeterminacy, right? What is the degree of indeterminacy here? 1, right? So I can pick a main system of my own choice. You can make this ruler, and you can make this ruler. Not both of them ruler. If both of them ruler, it's gonna be on a table, right? So one of them should be ruler. I choose here that this to be ruler. By the way, if you choose this one, it's still right. I mean like just this one, but this one is stay hinged. Okay, just pick one. All right, that's the main system. What I'm gonna do is the main system. Main system need to be stable and determinate. I'm gonna put the original loads on the main system, the 3 and the 6. What I'm gonna do is this, you are gonna get the reaction and draw the bending moment, shear, and normal. But right now, I only asked for bending moment diagram. Here, I said draw all the internal forces diagram. So you have to draw normal, shear, and moment. But I'm gonna deal, for the sake of time, with only the bending moments. For the reactions, you guys tell me, what is the horizontal reaction here? 3, right? But let me ask you something. At the end, what we are looking for, like from solving this, I'm looking for the horizontal reaction here that I removed, right? I made this from hinge to roller, so I removed the horizontal reaction here, so that's what I'm looking for. So at the end, once we solve this problem, do you think that the reaction here is gonna be 3?
No.
No, it's gonna be less or lower or bigger?
Less.
Less, why? Because this is gonna get some contribution from the X. You are pushing this frame. This one is gonna absorb some horizontal and this one is gonna absorb some horizontal reaction. So I believe that this one is gonna be a little bit less. Okay, but right now, since we make this main system, this one is taking all the 3. All right, then I need to find the vertical reactions. So to find the vertical reaction, get the moment here, you're gonna find this value, and this is gonna be 0.67. No, it's gonna be 2. That didn't make sense to me. 2 and 4. So first you take the moment here, you're gonna get this one, and then take sum of Fy, so you're gonna find 6 going down, 2 going up, so this one is gonna be 4. You found the reaction, draw the bending moment diagram. All right, so you guys tell me, what is the bending moment here? 0, right? How about the bending moment here? 6, why? Because it's gonna be 2 multiplied by 3. Is it positive or negative?
Positive.
Positive, because you guys remember, this is the sign. Positive moment is this way. You can draw it up or down, but just make sure it's positive. So this, and it's gonna be 6. How about the bending moment here? It's gonna be 2 multiplied by 6, which is gonna be 12, minus 6 multiplied by, 6 multiplied by 3.
It's gonna be 6 also.
It's gonna be 18, 18 minus 12 is gonna be 6, but it's gonna be negative. Up there, so we're gonna have a bending moment like this, and this is 6, and this is negative, this is positive. How about the bending moment here? It should be, this one should be equal to this one, so this is, both are gonna be 6, and if you wanna take the bending moment here, this is gonna be moment 0, and you end up with 3 by 2 is gonna be 6, and the moment here
0,
and here,
0.
all here is 0, because going down, there is no forces that can make moment. So that's also a negative bending moment, right? So we got what we called MO, the moment of the main system due to the original loads. Okay, so I finished this step, draw the bending moment diagram for the main system. Then step number 4, what should I do?
What about that roller?
I draw the same system again. I remove all the loads and then put unit load where?
And the roller.
At the removed redundant, I remove the horizontal forces from here. So I'm gonna put a unit load this way. I'm gonna make it 1 ton unit load. When you put this 1 here, absolutely, there's another 1 here, okay? A reaction. And then they both are gonna make a moment of 1 multiplied by arm 4. So I have to divide 4 over 6, and this is gonna give me 0.67 and 0.67. All right, but if you don't know how did I do it, take the moment here, and you're gonna find this reaction. And then take some Fy, and then you're gonna find this reaction. All right, so let's draw the bending moment diagram for this beam. You guys tell me, what is the bending moment here? 0. What is the bending moment here? 0.67 multiplied by 6 is gonna be 4,
Yeah.
right? So we're gonna have 0, and then I'm gonna connect it by -4 because this bending moment is that way. This is negative and this is 4. Same thing, you're gonna find this is 4 because it's gonna be 1 multiplied by 4, and this is negative. I drew M1. I did a step number 4, put unit load at each removed redundant and find M1. Okay, what is the next step? Calculate the deformation, delta 1O and delta 1-1. So let's do that. I'm not gonna remove this part of the board. Let's write here. Okay, so let's split it here. Check the camera. All right, so you guys tell me, how can I find delta 1O? Very simple, forget everything. The integration, this is 1, I'm gonna put M1. This is O, I'm gonna put MO, dl over EI, right? That's the rule. If you wanna find delta 1-1, what should I do? This is 1, I put M1, and another M1, dl over EI. This is how I find them. The thing is, I don't have I, but I have a cross section, 20 centimeter by 40 centimeter. So, you guys tell me, what is the I for this cross section? Let's say that this is B and this is D. It's gonna be BD cubed over 12. So it's gonna be 0.2 multiplied by point. By the way, I have here, this is centimeters, so let's keep them centimeters. So I'm gonna put 20 multiplied by 40 cubed over 12. It's gonna give me a number with a lot of zeros.
106,000.
How much?
106,666.67.
That's a hell of a number.
So 1 point.
Okay, so I have E, so I believe here I have only, okay, yeah, I have the EI. So at the end, like, tell me the number.
1 times 10 to the 1.
Tell me the number with 0, like
106,666.67.
Okay, so I'm gonna put EI here, and EI, once you multiply this number by E, so I have this as 10 centimeters squared. Just make sure that this is centimeters squared, this is centimeters. If I put this as a 10 meters squared, calculate this in meters squared. At the end, you will find that the value 2240 ton meter squared. I believe there's another 4 zeros, and if it's centimeters squared, but since it's meters squared, so I put it that way. Sorry, I didn't catch all these numbers.
No, it's okay.
Yeah. Okay, so, and then I have, what is next? I calculated EI, so right now I need to calculate M11MO. So let's do this. M1MO DL. All right.
Is that centimeters squared? Meters squared.
This is meter squared. Like it was a lot of zeros here, so I converted to be meter squared. Why? Because all my bending moment are ton meters. So this one needs to be ton meter squared. This is a little bit difficult. I mean, can you imagine? You think, oh, I'm gonna integrate this with this and integrate this with this. But the thing is, looking at the tables that we have from last time, we don't have this shape, right? We only have trapezoidal with rectangle, with triangles, triangles with triangles. So what should I do? I have what? I have to divide them into sections. So tell me, how many divisions that I need here? Three, right? You can do three. Like you can make this. This is one, and here, so you can use this 1, 2, 3. However, you can actually use two. This one and this one, because there is a triangle. Look that way. Like look here. I have this one, this triangle. Can you see how it's look? It's look that has this and this. Or you can use this one and this one and this one. That's fine. But when you integrate them, like if you pick this one, you have to come here and find the value here. And this value at 3 and 1.5, so you are gonna have, this is 3, 1.5, and 1.5, right? How did I know that this is 1.5? Because this is 6 and this is 6, so this is in the middle between this distance, all right? So the value here is gonna be how much?
3.
It's gonna be like here, 4. Okay, the value here is 2, this is 3, this is 4, right? It's gonna be 3. So you need to find out what are these values. So if you are gonna integrate this whole thing, you are gonna take this whole thing, this triangle. You be careful with that. And then you integrate with this. If you are gonna take this one, you need to take this one and you are gonna integrate a triangle with a trapezoid. Okay, you choose. Both of them are gonna give you the same answer. For this triangle, you have to come here in the middle and find the value here, which is 2, and integrate this triangle with this trapezoid. So let's do a bunch of them and see. How about you guys? Do you guys have the table? This one? Did I have it? Okay. I needed somebody maybe to guide me. Is anybody good with numbers? Like have this table? Do you have the table? This one?
I think I have all my.
Does anybody want to tell me? Do you want to look? Oh, okay, I have the iPad. Do you want to? Does anybody want to look here to follow what I'm gonna do? Do you want to? Okay. All right. So let's do it. Integration of M1 MO. This is MO and this is M1. Let's do them triangle by triangle. So I think I'm gonna need it. All right. If I have this triangle and this triangle, can you pick which rule I have to say? Like, is that 1/6?
One third.
1/3?
1/3 and 1
Okay, let me look because I need it. Yeah, because I will need to look. Okay, so I have. Oh, you are saying 1/6 or 1/3?
1/3.
Okay, this is the triangle and this is the
Oh, you're
triangle.
going
Okay.
with the whole
So
triangle.
M1 is this triangle, right?
Yeah.
And M2 or M3 is this triangle, so it's gonna be 1/6. Okay, so this should be 1/6. And then the moments that we have here is gonna be M1, M3. Let's see. M1 is 6. M3. Sorry, M3. M3 is, because M1 is the MQ, which is this one, so I'm gonna base
3
3.
3 and 6.
minus.
And yeah, we have to make sure if it's positive or negative. So actually what I can do, this whole triangle is positive and this whole triangle is negative, so I can put negative here and forget about the signs. Okay? So right now I have 6 and 3, so I'm gonna put them 6 and 3.
And the length is 4.5.
Interesting. So the length L plus C. So the length L is 4.5.
C is 1.5.
And C is,
1.5.
okay, no, it's not 1.5 because you have, oh yeah, here. No, the thing is, this is 3 and this is 1.5.
5.
Yeah,
Five.
D is the 3 and C is 1.5. I think like that.
The thing is, this triangle is, and the M1, okay, the C is the one in the opposite direction of M1, like this is the maximum moment, M, so M1 is in the side, okay, let me put it for you here. So this is also one point that you need to be careful with. This is the triangle that we have in the table. He says M1, and this one, let's put it that way, M3, all right? It calls this C, and this is D, and this is the whole length L. Look at this. M1 is here. If M1 is here, it's completely different rule. Okay? M1. C is the one that is opposite to 0 moment on this side. But look at the problem that we have here. The triangle is in the other direction, not in this direction. So let's draw our problem. Our problem is gonna be, I'm just gonna do this just to be careful what numbers you should pick. This is the one that we have in the tables. The problem that we have here, we have a moment like this, and this is 6, and we have a triangle like that. And this one is not equal, like you have something like this, and this one is 3, this is 1.5, and the whole thing is 4.5. All right, so my C right now is the one that meets the 0. So my C is this one. Can you see? This is my C. All right, so it's a little bit confusing. If you find out that this is a way it's gonna confuse you and dealing with this triangle, knowing which one is 0, you can actually divide this into 2 triangles and solve it as a 2 triangles. Like another way to do it, I'm just like want you to be careful with the numbers, because if you're making this triangle with this triangle, just look where is M1 and where is M3, because if M1 is here, it's completely different from M1 on the other side. Like here, this one, this is how our triangle is facing, the other triangle is facing that way. I'm gonna show you if we are gonna do it the other way. Let's pick this triangle with this triangle, a small one, and then this trapezoid with this triangle. So both of them are negative, so I'm gonna put negative. You guys look at the table and tell me, triangle with triangle is gonna be negative 1/3.
M1, M3.
M1, M3, that's very easy. I have M1 is 6, M3 is 2, 6, 2, and multiplied by the length, which is 3. This length. All right? I'm done with the first triangle. Second part is a triangle with a trapezoid.
1/6.
Look at this. Triangle with a trapezoid. This is 6, and the trapezoid is 2 and 3. Okay, the 6 is what we call,
This is the opposite.
this is M3, and this is M2, and this is M1. The tables are saying that if you have a rectangle with a trapezoid, it's gonna be 1/6 plus multiplied by M1 plus 2M2. But look, M1 plus 2M2, M2 is the one that is opposite to the number here. So that's my M2. That has, because right now I have one is M1 plus the other M multiplied by 2. So it's this moment plus this moment, but one of them is multiplied by 2. The confusing is which one I should multiply by 2. The one you multiply by 2 that has a corresponding moment on the other side. This one has 0, this one is not going to be multiplied by 2. So this is going to be M, this M plus this one multiplied by 2. And at the end, this is this part. And I have to multiply this by 6. Let's put here the 6. And 1 over 3. So 1 over 3, 6 multiplied by this plus 2 of this plus the length of 1.5. And that's negative. Why? Because this is positive and this is negative. Same thing we're going to do with these two things. I have a triangle and I have this one. So I have, both of them are, it's going to be positive. It's going to be 1 over 3. This moment is 6 multiplied by, which one is going to be multiplied by 2? This or this? If you guys look at the table, it's going to be 1. The 1 is going to be, this is 3 plus 2 multiplied by 4. Multiplied by the L 1.5. What did I do? So the table is saying, this is the rule. 1 over 6, M1 plus 2M2 multiplied by M3 multiplied by L. So since we have two moments here, 3 and 4, and this triangle has 6, so it's going to be this 6 multiplied by 3 plus 2 by 4. So we are finished. This moment plus something function in these two moments. Which one is multiplied by 2? The one that is opposite to a number here. So for example, if you use 4 plus 2 multiplied by 3 is going to be wrong. Because 3 has a corresponding moment 0 here. So you need to be careful which values that you are multiplying with. I know it's a little bit confusing, but you have to be careful when you are doing that.
Sorry, is it 1 over 3 or 1 over 6?
Yeah, actually both of them are, this one is 1 over 6.
Yes. Yeah,
And this one is 1 over 6. Yeah, it's confusing. And this one was a triangle and a triangle, so it's 1 over 3. Yeah, so both of them are 1 over 6, right? Okay, so we are done with the first part. How about this part? It's gonna be 1 over 6 because it's a triangle with a trapezoid. 1 over 6 multiplied by 6 multiplied by 2 by 4 plus 2. Is it positive or negative?
Positive.
Positive, because both of them are negative. And we have moment 6 multiplied by 2 plus 2 by 4. And all of this is going to be multiplied by 2, which is the length of the beam. How about this triangle?
0.
Why? Because I have 0 here. So 0 multiplied by whatever here is going to be 0. So I'm done with all of them. And then at the end, you're going to put the final calculations. Delta 1 ohm .01026 meters. All right, so I believe the only difficult thing here is to decide, is to master how to use this table, how to integrate triangle with a trapezoid, to make sure that this number is meeting this number, so that the number that is multiplied by 2, and this one is going to stay the same. All right, same thing, you are going to integrate M1 with M1 DL. How can I do that? That's very, very easy. M1 or delta 1 is the easiest part because it's just two triangles. You are going to integrate them with each other. So if you look at the table, two triangles is going to be 1 over 3, and it's always positive. 1 over 3, M1, M3, so it's going to be 4 multiplied by 4 multiplied by the length 6 plus 1 over 3. And then you have 4 multiplied by 4 multiplied by the length 4. How did I do that? I go here, triangle was triangle, this one, integrate this and imagine that you have another beam that has the same bending moment. That's M1 and that's M1. Okay, this is 6 and this is 4. Integrate M1 with M1. So you integrate this triangle with this triangle. This is 4, right?
4 years.
Yeah. So this triangle with this triangle is gonna be 1/3 M1 M3, so 4 multiplied by 4 by the length 6. And same thing, 1/3 4 multiplied by 4 multiplied by the length 4. Okay, so once you do this, it's gonna be 0.0234. Does anybody have any questions so far?
Just to clarify, the MQ is the on the table. That's MO.
MO. We don't have Q anymore.
Yes, that from the table is MQ, right?
Yeah, no, MO, where's the table? MO is the M1, like, no, sorry, MQ is the M1, 1 means the virtual load. MB is the main load, that is the 0, okay? So here you will find it, Q is 1, and B is the original load, okay? Like that's, if you go back to the concept of virtual load, but right now we are not calling Q and B. We're calling 1 or O. 1 means virtual, O means the main load. All right, so we are done. We got delta, but by the way, yeah, I need to put something here.
That's dividing by EI, right?
Yeah, exactly, that's what I want to say. The value that I put here is the integration of M1 DL over EI. That's the final value, after you get this value. And the value that I got here is the integration of M1 MO DL over EI. I mean, after I divide with EI, like calculate this, divide by EI, you get this value. And once you are done, you divide by EI, and we already calculated EI here. So finally, I'm sorry, I'm swapping between because I have the numbers here and then. Okay, finally you substitute like this step, apply the compatibility equation, delta 1O plus F, delta 1 equal to 0. So F is gonna be equal to this one, which is gonna be negative 0.01026 divided by 0.0234 when you send this the other side, and the final force is going to be negative 0.452. When I did it yesterday, it was negative 0.45, and if you included all these components, it's going to give you 2 at the end or something. All right, so right now I find the reactions. So I have right now, this is my beam. I have a hinge here and a hinge here, and I have a load 6 and 3. And I know what is the value of the reaction here. It's equal to, by the way, I assume the unit load going this way, right? It's 1. But when I got the final reaction, it's a negative. That means that my assumption is not right. It should be that way, and it should be 0.452, and that makes sense. Because when you push that way, they have to be the other way. So I found this was 3 before. Right now, this is gonna be 2.5.
40.
Let's put here 5. Okay, 2.55. That's when you get the reaction. And then you get some of the moment here. You will be able to find what is the reaction here and what is the reaction here. So this is gonna be 2.3, and this is gonna be 3.7. I found the reaction for the entire beam that is determinant, and then you can draw the bending moment diagram. So when you draw the bending moment diagram, you can use this reaction to draw the bending moment diagram. Like get the moment here, and to get the moment here is gonna be 2.3 multiplied by 3. So the moment here is gonna be
6.9,
6.9.
9.
Yeah. And then when you get the moment here, it's gonna be 4.2, and the moment here is gonna be 4.2, and then you're gonna get something like this and something like this. This is gonna be 0.9, and that makes sense because if you take the moment here before the reaction here was 0, right now the reaction is 0.45, 0.45 multiplied by 2 is gonna give you 0.9, and that makes sense with something here. And there's another way that I can do it. How? M final is equal to MO plus F multiplied by M1. How? Get the value from this bending moment. This is 0, and 0 is going to give you 0. It's going to be 6 minus 0.45 multiplied by negative 2. Like, let's find out M1. MF is going to be 6 minus 0.45, which is the value of my reaction, multiplied by the negative moment that we got it from M1, it's 2. So you'll find it's a negative, so it's going to be 6 plus 0.9 is going to give you 6.9, which is the value here. You do it here, the same thing. MF at 0.2 is going to be equal to 6, same thing. 6 minus 0.45 multiplied by negative 4
4.2.
is gonna give you, is it 6?
4.
I got the moment here, I need to get the moment here, right? So you need to find the value of the moment here. So yeah, I mean, like, once you are done, you are get this 4.2, and you can get this one and the other one and apply in the same rule, okay? So does anybody have any questions so far?
Are we gonna have frames in the exam?
Maybe. I mean, this quiz,
Oh, in the exam.
the final exam, yeah, maybe, because I have frames here. So it's not about frame or beam. It's about how many redundants. Since it's only one redundant, it's easy. Yeah, beams maybe because you don't have legs and stuff like this, but since I have it here, I believe if you practice, you're gonna find it easy, okay? All right, but I mean, like, I'm gonna give you one that is gonna be sufficient to be done in 30 minutes, like not one that is like 3 degrees of freedom and gonna take a lot of time, all right? Okay.